Hello students, in this video we are going to see subspaces of Rn. Subspaces of Rn. Okay. Definition. A subset H of Rn is said to be subspace of Rn if it satisfies the following three properties. First property is the zero vector is in H. Second property is for all u bar and v bar in H, the sum u bar plus v bar is in H, that is for all u bar comma v bar belongs to H, u bar plus v bar belongs to H. Okay. Third one is for all u bar in H and for all scalar alpha, the vector alpha into u bar is in H, that is alpha into u bar belongs to H for all u bar belongs to H and alpha is any scalar or alpha is any scalar or alpha belongs to set of all real numbers. Okay. A subset H of Rn is said to be subspace of Rn if it satisfies following these three properties. First property is zero vector is in H. If you take any two vectors in H, their addition must be in H, second property. And third property is alpha into u bar is belongs to H for all u bar belongs to H and alpha is any scalar. Okay. Let us write down one remark. Remark is a subspace of Rn is a subset of Rn. Subspace of Rn, it is a subset of Rn, but which is closed under addition. Closed under addition means if you take any two vector in H, their addition must be in H, and scalar multiplication. Closed under scalar multiplication means what? Alpha into u bar is belongs to H. For all u bar belongs to H, alpha is any scalar. Okay. Let us take example on subspace of Rn. Example: for vectors u1 bar, comma u2 bar and so on up to uk bar in Rn. Okay. The set S of all linear combinations linear combinations of u1 bar, u2 bar and so on up to uk bar is a subspace of Rn. Okay. Here we have to solution. Here we have to show that for vectors u1 bar, u2 bar and so on up to uk bar in Rn, the set S is nothing but the set of all linear combinations of u1 bar, u2 bar and so on up to uk bar is a subspace of Rn. What is set S? Set S is the set of all linear combinations of u1 bar, uk bar, u2 bar and so on up to uk bar. Means that set is of the form alpha 1 u1 bar plus alpha 2 u2 bar plus and so on up to alpha k uk bar. Okay, such that alpha 1, alpha 2 and so on up to alpha k are scalars. Means every element of this set S is of the form alpha 1 u1 bar plus and so on up to plus alpha k uk bar. Okay, and we have to show that this set S is is subspace of Rn. That is, we have to prove three properties of subspace. First property is zero vector in S. We have to show that. Second property, u bar plus v bar belongs to S for all u bar comma v bar belongs to S. And last one is alpha into u bar belongs to S. U bar for all u bar belongs to S and alpha is any scalar. Okay. First we show that zero vector in S. This is obviously clearly the zero vector belongs to S. Why this is? Because since 0 bar can be written as 0 dot u1 bar plus 0 dot u2 bar plus and so on up to plus 0 dot uk bar. Means 0 bar can be written as linear combination of u1 bar, u2 bar and so on up to uk bar. Therefore 0 bar is belongs to S. Hence first property is satisfied. Now we have to show u bar plus v bar belongs to S. For all u bar, v bar belongs to S. Okay. Suppose this is the first property. Second, let u bar and v bar be any vectors in S. Okay. Then what happens? U bar can be written as linear combination of u1 alpha 1 bar plus and so on up to alpha k uk bar, obviously because u bar belongs to S. And v bar can be written as linear combination of u1 bar, means v bar can be written as beta 1 into u1 bar plus beta 2 into u2 bar plus and so on up to beta k into uk bar. Okay, where alpha 1, alpha 2 and so on up to alpha k, beta 1, beta 2 and so on up to beta k are scalars. Okay, we have u bar plus v bar is equals to, what is u bar? U bar is alpha 1 u1 bar plus alpha 2 u2 bar plus and so on up to plus alpha k uk bar plus beta 1 u1 bar plus beta 2 u2 bar plus and so on up to plus beta k uk bar. Okay. Observe these two terms. In these terms u1 bar is common, so in bracket remains alpha 1 plus beta 1 into u1 bar. Okay. Observe these two terms. Here u2 bar is common, so take it as common. So in bracket remains alpha 2 plus beta 2 u2 bar plus and so on up to plus. In these terms uk bar is common, so in bracket remains alpha k plus beta k into uk bar. Okay. Alpha 1 and beta 2 are two scalars, so their addition is also scalar. Alpha 2 and beta 2 are scalars, so their addition is also scalar, and so on up to alpha k and beta k are also scalar, so their addition is also scalar. Means u bar plus v bar can be written as linear combination of u1 bar, u2 bar and so on up to uk bar. Therefore u bar plus v bar is a linear combination of u1 bar and so on up to uk bar. Therefore u bar plus v bar belongs to set S. Okay. Now we have to prove property third. In third property we have to prove alpha into u bar belongs to S for all u bar belongs to S and alpha is any scalar. Okay. Alpha into u bar. Okay. Okay. Take here beta into u bar. Okay. Beta. U bar is in S, so u bar is of the form alpha 1 u1 bar plus alpha 2 u2 bar plus and so on up to plus alpha k uk bar. Okay. This is equal to beta. This can be written as this beta multiplied by this beta, so here you will get beta into alpha 1 u1 bar plus beta into alpha 2 into u2 bar plus and so on up to beta into alpha k uk bar. Okay. Students, this beta and alpha both are scalars, so this can be written as beta into alpha 1 u1 bar plus beta into alpha 2 into u2 bar plus and so on up to beta into alpha k into uk bar. Beta and alpha 1 both are scalars, so their multiplication is also scalar, and so on up to beta and alpha k both are scalars, so their multiplication is also scalar. So beta into u bar can be written as linear combinations of u1 bar, u2 bar and so on up to uk bar. Therefore beta into u bar is a linear combination of u1 bar, u2 bar and so on up to uk bar. Okay. Therefore beta into u bar is belongs to S for all u bar belongs to S and beta is any scalar. Okay. Therefore S satisfies all three properties of subspace. All three properties of subspace. Therefore, S is subspace. Therefore, S is subspace of R3. Sorry, S is subspace of Rn. Notation. We will denote the subspace S in above example by span of U1 bar and so on up to UK bar, and say that span U1 bar and so on up to UK bar is the subspace spanned by U1 bar and so on up to UK bar. Write down one note. From the definition of a subspace, the Rn and the singleton 0 bar is 0 vector are subspaces of Rn and are called trivial subspaces of Rn. Means Rn and singleton 0 are trivial subspaces of Rn. Let us take next definition. Column space of a matrix. Definition. The column space of a matrix A is the set column space of A. It is denoted by COLA of all linear combinations of the columns of A. The column space of matrix A is the linear combinations of columns of A. Okay. Note, if A is equals to matrix U1 bar, U2 bar and so on up to UK bar, B m by n matrix with columns in Rm, then column space of A is same as span of u1 bar, u2 bar, and so on up to un bar. It is clear that the column space of an m by n matrix is a subspace of Rn. Okay. Let us see one example on column space. Example, let A is equals to matrix 2 minus 3 minus 4 minus 8 8 6 6 minus 7 minus 7 and B bar is equals to matrix 6 minus 10 11. Okay. Determine whether B bar is in column space of A or not. Determine whether B bar is in column space of A or not. Okay. Solution. The vector B bar is in column space of A if and only if B bar is a linear combination of column of A. Okay, by definition of column space of A, that is if and only if B bar can be written as A into X bar for some X bar. That is if and only if the equation A into X bar is equals to B bar has a solution. Okay. Means B bar is in column space of A. When it is possible? When A into X bar is equals to B bar has a solution. Okay. What is A? A is matrix 2 minus 3 minus 4 minus 8 8 6 6 minus 7 minus 7. Okay. Into x1 x2 x3. Okay. Which is equals to B. B is 6 minus 10 11. Okay. Consider augmented matrix. Okay. Augmented matrix is 2 minus 3 minus 4 6 minus 8 8 6 minus 10 6 minus 7 minus 7 11. Okay. Students, you have to homework, that is obtain its reduced row echelon form. So row reduced form is matrix 1 0 7 by 4 minus 9 by 4 0 1 5 by 4 minus 7 by 2 0 0 0 0. Okay, from this last matrix we can observe that A into x bar is equals to b bar has a solution. See here column 3 has no leading one, so x3 is a free variable. Okay, or here we can say that from last matrix means this, we can from last matrix shows that A into x bar is equals to b bar has a solution. Or you can say here this matrix shows that A into x bar is equals to b bar has a solution. Therefore, b bar is in the column space of A. Column space of A. Okay. Students, always remember that any vector in column space of in matrix means we have to show that A into x bar is equals to b bar has a solution. Okay, we will stop here. Thank you.